Hey guys, so in this video, we've got a function that we are going to be talking about. And I know this sounds a bit, more mathy, but by the end of this video, we will relate it back to quantum mechanics, and we're actually going to get a really, really, really important result. And so, let's get started. So the function that I want to talk about, you may have heard of this before, and it's a pretty weird function, actually. It's called the Dirac delta function. And named after the Greek letter delta, but also the famous physicist Paul Dirac, um, who made a lot of great use of this function. So I'm writing it. I've got delta. This is a lowercase Greek delta, delta of x, and this function is defined in the following way. It's defined such that the function is 0 if x does not equal 0. And it is infinity if x is equal to 0. Right? So it's not super hard. And then delta of x minus a, which is another useful form of this, right? Well, it is 0 if x minus a, right? Because if the argument, this is the argument x minus a, this is the argument. If x minus a, if the argument is not equal to 0, which means x is not equal to a, right? And it is infinity if the argument is equal to 0, which would mean x would be equal to a, right? So I'm going to go graph this. And I'm obviously not going to be able to graph it all the way up to infinity, but I'll do my best. My best would be just graphing it off the screen. Okay, so I've got, this is 0, and this is a, right? A can be anything. And if we think about it, the Dirac delta function, I'll do the delta function in green. Delta function just looks like this, right? Right, this would be delta of x, right? And the delta of x minus a is just shifted over to the right a, right? And it would look something like this. Right, and in the future, and generally this the function is sort of graphed like this, so you can sort of see a little bit more of its properties. It's usually graphed something like this. So if I've got, this is a here, we actually, I'll redraw that because it's not, it's harder than you think to draw this. So this is, or a. It's usually drawn sort of like this, where this is sort of at infinity, right? And this is infinitesimal, right? Now, this seems sort of just a weird function to draw, right? But it does have some uses. And so I'm going to I'll just leave this up here. There's no way to really erase around this, so hopefully you can still read it. I'm just going to redraw this. Oh no, forgot to label this delta of x minus a. So on another set of axes, I've got 0, here's a. Right, and a can be negative 2, that would just put it to the left of 0, right? And graphing this, right? And this goes all the way to infinity, right? So, infinity is not really there, but, just believe that for a minute. So the delta function has an interesting property where this area, right? You may ask, how could we define that area? It seems like, if we're doing that Riemann something, it's one rectangle. Its width is 0, right? It's just around A. its width is 0 and its height is infinity. Its area would be 0 times infinity, which is indeterminate, right? So when we're defining the delta function, we actually define it like this. This is part of the definition of the delta function. And it turns out, given this definition right here and the following definition, you can actually take and derive a ton of different properties from the delta function. And there's also different definitions. There are many different definitions that mathematicians and physicists use. But in general, it's a really important function. We'll actually see more definitions as we get later in this course. But this definition is that the integral from negative infinity to infinity, I'll rewrite that, the integral from negative infinity to infinity of delta of x minus a dx, right? The area under the delta function, right? The total area under the delta function is equal to 1. That's just how we define it. And you'll notice that this could also be, because all of the area is right at a, if we take the integral from a minus epsilon, where epsilon is just a little number, to a plus epsilon, so you may say a minus epsilon was really close to a and a plus epsilon. All the area is between a minus epsilon and a plus epsilon. All the area is, an epsilon can get as close as you want to a. All of the area is right at a. So the integral from a minus epsilon to a plus epsilon of delta of x minus a dx still equal to 1, right? Because all of the area is under that. So this definition is just saying the area of the spike, right? This area is equal to 1, right? That I drew in here. So that may seem like a pretty weird definition, but it's going to end up to be really, really, really useful. So, now I'm going to note something. This is going to bring this back. Actually, hold on. Before I do that, apologize about that. I'm going to erase this. See what I can erase here. I'm just going to have to, I think, put up with these. See if I can erase around this. There we go. Okay. So, another quick note, that if I have some function of x, and I'll do this in a different color. If I've got some function of x times delta of x minus a, then this is equal to, well, let's look at it this way. When x does not equal a, right, this thing is just 0, right? The only time that this term will not equal 0 is when x equals a, right? So this would mean that this is the same thing as f of a times delta of x minus a. What I mean by that, right, and we'll just look at this, compare the two. This is equal to f of a times delta of x minus a. So this is equal to f of a times delta of x minus a when x equals a. And this is equal to, and it's equal to 0 when, or if, this is equal to 0 if x does not equal a, right? And I know this is sort of tricky way of writing this, but this just but if we look at this side, right, this side is also, it's obviously f of a delta of x minus a, always, but also when x equals a, and it's 0 if x does not equal a, right? So this is a pretty subtle point, but it is really important that this property of the delta function is true, right? F of x times delta of x minus a is equal to f of a times delta of x minus a, because if x does not equal a, then it's 0, right? Which 0 equals 0, right? So this is true whether or not x equals a or x does not equal a, right? For any values of x and a, this identity is always true, and you can sort of test that out in your head, right? Look at how different values would be. It's always going to be the same, right? Whether or not x equals a or x doesn't equal a. So, and actually, I'm sorry, I forgot one more property of the delta function before we move on to the quantum mechanics of this. I just want to note delta of x minus a is equal to delta of a minus x. So delta of x minus a is even. So, and you can just look at this from the definition, right? Here, we're just literally switching the place of x and a. We're swapping them, right? And so this would be 0 if a does not equal x, and infinity if a equals x, right? So, which is just the same thing, right? X is not equal to a, and a is not equal to x are the same thing. X equals a and a equals x are the same thing. Okay, so hopefully you guys have all these properties down. I'm going to keep some of this up, but I'm going to erase what we just did. And now to relate this back to quantum mechanics. Well, we have it's sort of like a distribution, right? Right? This seems like the wave function, right? That's what we'll call the state function, phi a of x, right? Because if we're looking for a function with a definite position, it would look just like this, right? Because it's infinite at this one position, we'll call it a, right? And 0 everywhere else, right? It should make sense that this would be the state with the definite value of a, right? And it's a function of x, and we'll get to that in a little bit. How it makes sense that this is a function of x, right? But this is equal to delta of x minus a, right? Again, hopefully this makes sense that the function with a definite position x equals a, right, is this Dirac delta function, right? And using this, and if you just trust me on this one, we'll derive a few very, very cool properties. So we know from our superposition that psi is equal to the integral from negative infinity to infinity of CA dx, right? And I'm going to rewrite the property I forgot. I do need to keep this up here. F of x times delta of x minus a is equal to f of a times delta of x minus a. So, back down here in our red, well, this is equal to, in this case, it's negative infinity to infinity of c sub a delta of x minus a. Oh, sorry, and this is dA. Hopefully you caught that. So this is now equal to, right? Well, if we look at this c sub a, this is a function of a, right? C sub a is it's called a probability amplitude. It's right. It's because it's norm squared is the probability density. So C sub a is a function of a. It doesn't depend on anything other than what a is, right? This is related to how probable it is that the particle's at a. So it makes sense. It's a function of a, right? But we'll notice, right, we can work the other way around. A function of a times delta of x minus a is just, right, this would be the same thing, negative infinity to infinity of c sub x times delta of x minus a dA, right? But now c sub x, right, just because we can switch it, that's the property of the delta function. Now c sub x is not a function of a, it's only a function of x. It can get taken out of this integral, right? Because it's a constant with respect to a, right? So this is equal to c sub x times the integral from negative infinity to infinity delta of x minus a dA. And notice that this integral is equal to 1, so this is c sub a. And I don't know if you see how significant this is, but what we just derived is psi, which is evidently a function of x, is equal to c sub x. This is really, really significant, right? So first of all, we notice psi seems to be a function of x, right? We also notice that the function with a definite value of x is a function of x, right? This function, this is a wave function, is a function of x. Our wave function, our state function, psi, is a function of x, right? And there's a few other things that you may not sort of see with this. So now I'm going to erase the stuff that we have in the delta function. And I'll put back the, I accidentally erased a few things. Nope. To have the pen there. And there we go. So we now know, right, the probability density of x, of the particle being at x, is equal to the value of the wave function, psi of x, norm squared, right? Which is equal to the wave function complex conjugate times psi itself, right? And I think, I don't remember if I mentioned in the last video, but we're still working in complex numbers, right? Psi can be complex. The wave function is it's a complex valued function. We then know the probability, the particles somewhere between x1 and x2 is the integral from x1 to x2 of psi norm squared dx, right? And then, just using the idea of normalization that we had, well, what's the probability that psi, right, is, or the particle is somewhere between negative infinity and infinity? Well, that's the integral from negative infinity to infinity of psi norm squared dx, which is equal to 1. And this is our normalization condition. Similar to how in the other case we had, right, the magnitude, psi had to, be a unit vector. The magnitude, or the norm of psi had to be 1, right? That's sort of what we're doing here. And if you think about it, this kind of does make sense that this is a norm. We're adding up, right? This is sort of like this is sort of like saying the norm squared of psi is equal to 1. We're adding up psi squared for all possible values of x, just like when we're doing this, we're adding up, each component of psi squared, or norm squared. All right. So we can then write, we can show this, right? Just like with our last the last video that we had, right? Psi of x, because psi is is evidently a function of x, is equal to the integral from -infinity to infinity, the sum over all possible values of q of c sub q, right, which is just a function of q, times phi sub q of x dq, right? And so phi sub q of x, right? Phi sub q is the wave function, is the state function with a definite value of q, right? But since we know state function is a function of x, a wave function is a function of x, I'm gonna stop calling them state functions, just calling them wave functions. This, right? This is a wave function. Wave function, that's how I'll abbreviate function, with big Q equal to little q, right? And it's a function of x, because wave functions are functions of x. So, and so then we can express the psi as a superposition of c sub q times phi sub q, right? The other thing that we know, right, because we see that a wave function has to be normalized. The question is, does this wave function have to be normalized? Right, because we remember the superposition only worked in an orthonormal basis when we did the vector spaces. And the answer is actually no. And we're going to be talking about that in a few videos. Specifically, why this actually really shouldn't be normalized. And then that's kind of it. It seems sort of counterintuitive, but we will see that. That's an exclamation point, not a question mark. So hopefully that makes sense. The last points that I just made, which is psi of x is this coefficient function, right? And so then we can do all this. We know the wave functions are a function of x, right? They're not just some. In the last video, I didn't put of x because they were just some function. We didn't know what the variable was or anything, right? We also know, just like in the discrete case, we can write the waves the state vector in different bases, right? And we'll actually find out that later we'll be able to do that with the wave function. It's not necessarily a function of x. We can write it in different bases. But when we're writing psi of x is the wave function in the x basis, right? And a good way to think about that, given, so let's say we're writing some function in, I don't know, the energy basis, okay? And this is back in, with the vectors, right? Psi is equal to C1 times the wave function, or the state vector with energy E1, right? Plus C2, the energy E2, C3, energy E3, right? These are, or actually, why don't we just call it with the 3, just for simplicity. And note, these states, this is not actually just the energy value, this is the state with an energy E1, state with an energy E2, state with an energy E3, right? Well, this function is written in the energy basis because if, say, we're given E1, we can tell you what the probability of E1 is just by looking at the wave function, which is, C1 norm squared, right? Well, just like now, when we write psi of x, and I'm going to erase this thing at the bottom. Hopefully we've got that down. If not, you can rewind and write it down. When we write psi of x, right, we're given x equals, I don't know, x1, right? We can tell you right away, not the probability, but the probability density of x1 is psi of x1 norm squared, right? Just by looking at it, right? And so that's sort of why psi of x, this is actually written in the x basis, right? Because when we're written in the the energy basis, right, it gives us all the information we need right away without having to do any inner products or anything. Right away, what the probability of having a certain energy is, just like when you're written in the color basis, right? It told us right away, using just the coefficients, what our probability of it being white or black is, right? Well, when we write psi of x, right away, if we've got this function, we know the probability density at any point x. So this is written in the x basis, right? So this is really, really important. Okay, so hopefully this wasn't too confusing. I know we did a lot this video. You saw the normalization. You saw this result. These results are really, really important. Okay, and then using the Dirac delta function, the other thing that we realized in this video is that phi sub a is equal to the delta function, delta of x minus a. And if you still don't buy it, just think about it a little more. If we're trying to build this function, a wave function with a definite value of x, we would want it to look like just a spike at, x equals a and 0 everywhere else, right? And because now that we know the wave function's probability density, right? The probability density, it's infinite here. It's, it's a probability of 1 divided by an infinitesimal area, right? That makes sense, that the probability density, right, if the wave function, if psi equals, no, that's the last thing I'll write this video. If psi equals phi a of x, which is equal to delta of x minus a, the probability density of a is infinite, right? Because it's, it's the delta function norm squared, right? Because this is probability of 1 divided by the probability of 1 divided by the length 0, right? The probability isn't shared but in any length. It's an infinitesimal length, right? This is infinite. Okay, so hopefully that makes sense. If not, I usually, don't advise you sort of just to take something on faith, but this is so important. I can try to possibly explain this better in other videos, but I think I got it pretty well. Is as intuitive as the Dirac delta function can be, which is not very intuitive. So given that, I will see you guys in the next video.